next speaker is Matteo Calabrese from the Norwegian University of Science and Tech. This summer he'll be graduating from Aalto University and NTNU with a master's double degree in security and cloud computing. And while being a student in this field, he had the opportunity to work on space systems and found his passion in securing orbital technologies for the future, which is very encouraging to hear. And with that, the stage is yours.
Okay, better? Yes. Hi, everyone. So, yes, I'll be picking up the topic that Johannes and also Brendan Bailey spoke about earlier. So my focus is on CubeSat specifically. I got my introduction, I guess skip right into it. So this is what we'll be looking at today. I'll just briefly explain why my focus is on CubeSats and why I believe it's important to take a look into their security. I'll be making a case about OPSSat, the very successful mission that the European Space Agency recently had, launched in 2019. Explain a little bit how they work with what they developed also for that mission, which is the NanoSat MO framework. And then we'll be taking a quick demo. There will be some terminal work, but don't be intimidated. I have the dark theme on, but it's nothing complicated. I'll walk you through it, and then we can draw conclusions. So let's see. I believe this is a very important time for CubeSats. We've been seeing a lot of improvements recently in technologies. We can talk about COTS, we can talk about all the computer power that we're able to cram into these vehicles. Ground station as a service has been a very hot topic now for the whole conference, and we know it's growing rapidly. And also ride sharing means that we're able to launch this mission with very reduced costs and with very different timelines compared to before. So what we draw from this is we're starting to see a lot more constellations, a lot more interconnections between satellites, even if they're quite small. A lot of software being run on board compared to what we had earlier, which was a very basic, we can call it IoT device in space, running just a few commands. The continuous coverage lets us control the missions and get way more data from it, be that image acquisitions, telemetry, whatever kind of study we're running on them. And then with this new OPSSat, we kind of introduced the concept of on-demand missions, and I'll explain in a little bit why. So why is this the prime example of my talk and of the kind of outlook on CubeSats that we're having today? Well, in just 3 units of CubeSats, ESA managed to put a lot of different and interesting toys in this CubeSat. It was mentioned yesterday by Johannes a little bit. What they were trying to challenge us, the has never flown will never fly. So obviously we know that with space missions, the risk of failing emissions is usually not worth a game. So we end up never trying cool things in space. And this is exactly what they were trying to address. And I guess they succeeded immensely. So what happens is we have a flying lab, which is an actual flying lab. So it's open to all. People can sign up as experimenters and run their experiments on space. We can develop applications, for example, using the NanoSat MO framework, which is a framework, open source framework released by ESA, which lets us literally run Java applications as well as C application, Python applications on the satellite on this very interesting payload, which is the SEPP, the SEP, Satellite Experimental Processing Platform, an actual, basically, computer, Linux embedded computer. So what we can do with this framework, or even without, because it's not mandatory to use, it's use all payloads and the whole spacecraft as an API. So we have very easy access to all the payloads, either through Java or through other programming languages and technologies that we choose to use. And with the whole suite, we can develop our application, test it on ground. It comes with a simulator, CubeSat simulator, that it manages to emulate all the payloads on your local machine. And then what we can do is package it, test it as if it were on the real satellite. Then we submit it, and then we can control it. So this is the process of as an experimenter a little bit more in detail. We can develop, then we try it on local machine that we submit it to ESA. ESA will run their tests, make sure that it works, the integration tests, try it on the FlatSat, try it on the very realistic models of the satellite. And then once they upload it, we can very much easily connect to it through a very convenient GUI even. Run commands to it, check logs of our application, check logs of what we're doing, publish data back on Earth, and even, for example, get an SSH terminal into our application and into the system. So stuff that we haven't really been seeing before. But we security people like to dwell on the but a lot. This means that this very cool mission introduces a lot of complexity, be that with the architecture, be that with the software, be that with the numerous open source technologies that it employs, and commercial off-the-shelf components. So it is important that we take a look at what can happen if things go wrong. And They usually don't, but until they do. So just a little disclaimer, ESA is collaborating with me on the study. So I was given a production image of the payload, of the main payload, which is the SCPP, the experimental platform. And I managed to run, just like Johannes and their team were trying to emulate the bus system and the firmware, I was trying to run the actual satellite image that runs on the actual experimenter platform image on my computer to run tests and to check for vulnerabilities. And this is what I found. So let's try and do a little attack. This is what I thought about presenting for today. We'll be targeting specifically the camera payload because I think it's funny and it's quite exciting to spoof or to play around with a camera. So what experimenters and applications can do on a satellite usually is access it either through the framework that we saw before, through a Java application, very convenient, but also through like a CLI binary, an application that's on the file system. So what I succeeded in doing, I wanted to try and see if I could execute code or escalate privileges on the satellite, on the system, or even do a denial of service of the payload, or why not even the whole satellite or experimental platform. The technique that I'm using is library hijacking. Some security people might be familiar with it. If not, I'll walk you through it. It's nothing too complicated. The goal of the attack was to showcase how it's not really necessary to have a big background in security, but it can be accessible to what we call script kiddies. It's a script kiddie kind of level of attack on purpose to show that it's not really necessary to be a staked actor, attacker, because I'm not. Maybe I'm not. Where am I? So yeah, we'll go through the mitigations also at the end, obviously. So give me a second. I'll pull up the terminal. Okay, I'll try and do it with both hands. So I have this image running in a container. So this is more or less what it would look like to have a shell inside the main payload, the experimenter platform. Usually this is complicated. Usually experiments have their own home folder. And for example, we can see here there are a few that I deployed. Let's say that this is my application, experiment 123. This is more or less what it would come. This is just a filler files. It looks like it would look like if it showed, but it doesn't. Is it me or? I didn't sacrifice enough animals to the demo gods last night. I can try and plug it out and plug it in again. Or maybe reboot it. Or maybe not. The attack is not that dangerous, it's okay. It shouldn't, at least. Yeah. Yes, great. Thank you very much. So this is what will look like more or less in an experiment folder. I have my configuration parameters that the framework creates. Most of it is automatic. But in lib, for example, I have my library and I can put my dependencies. Let's say I developed an application that I want to look legitimate and send it through ESA ESA onto the satellite. And by obfuscation or by human error, I managed to deploy something malicious with it. Let's say that it's very discrete and it's not really easy to detect. So what I can do, for example, is I'm using a very easy and straightforward script from GitHub that I found to create a payload and exploit library that I will use against the camera API. So the way it works is, for example, we can I'll show you briefly how the invocation of the camera works. So it's just a binary. This is what it would look like to take a picture. Let's say we just call it with no arguments, and you can see that it works. Well, it doesn't, but it executes. So we can also check, for example, what this binary is using for libraries, or if it is using any shared binaries for shared libraries or shared objects in Linux. For people that don't know, are basically way to delegating code, portions of code, a portion of functionality to a different kind of file, so that it's easy to maintain and easy to update. So we just swap it in case of updating the whole main program. So with this, we can check what library the binary is using, and luckily we have one that is kind of interesting. So most of them are, I hope you can see, I can make it bigger. Most of them are classic libc, libgcc, but one very interesting one is libims 10100 API, which looks like something that the camera definitely needs to work. So we can see where it is. And so let's see if there's something interesting in there. What I do now is pull up the objects that are defined, or the functions and the symbols that are defined in this library, to see if there's something I can use for my attack. So we go into the and we tell it to dump the dynamic symbols. Maybe if I spell it correctly, it will work. Or maybe not. Sorry. Just let me take a look at how it's supposed to be written. Sims, yes. Is there a space that I'm missing? Oh no, there's a double dash here that I'm missing. I'm sorry. Yes. Okay. Can you please? Oh yes, there's missing an extension. There you go. I'm sorry. So here we see the functions and their symbols that are defined in the shared library. And while some of them are classic functions taken from libc, classic prints or memory copy, string copy, we don't need really those. We don't really need those. But we find it interesting because there's some stuff that could really be useful for an attack. We see that there are some functions like init or set gain, stop continuous done. We definitely see USB open, so something that the camera is using to use the payload and actually engage and start taking pictures. So what I can do here with the simple script that I mentioned earlier is, for example, I'll just copy the command so that I don't get those mistakes again. What I can do with this very simple script is create a different library, which is a malicious library, that contains the exact same symbols and function definitions that the original library contains. So when, and then I'll try to feed that to the linker, or I'll try to feed that into the binary, so that when the binary calls the functions that it needs to actually perform the operation that it does, it will look up the functions and the implementation of them in my library instead of the original library. And we'll see what that can cause. So if this works correctly, and it does, luckily, we can see that the payload, that the script is just creating empty, in this case, functions just to keep the functionality of the original binary. And we can see, yes, I'm sorry, I'll generate it again without the output. We can see that we have our new library here, same name as the original one. If we dump the symbols, it's going to have the same symbols as the other one, because that's the whole point. So now what I'm going to do is try and execute the same binary that I did before, but specifying and asking the system to load our library, or the malicious library, before the original one. And so we go. Okay, we can see that the binary executed just like before, but there's something else, something extra. We have a little system with a little echo here that just says that the library has been hijacked. So we managed to successfully run code and applications at the same time. This can be weaponized a little bit more. This was just an echo example, but if I have like a different type of attack, just a little bit more dangerous, but nothing too crazy so far. And this, for example, we'll do the same thing, but this time it will, yeah, we had no message. But if we go into a target experiment, let's say that we want to target another experimenter that is running stuff on the satellite, then we can see that, let's say that they use the camera to take a picture. We can see now that there's a captured JPG. So we can pretend that the camera worked and that the payload returned an image, but we spoof, essentially, the payload to return whatever we want. Now, this is just an empty file, obviously, for demo purposes, but it can be weaponized to be much, much worse. And yeah, since we're basically executing code as root, because this is the problem with the actual configuration on the satellite experimenter platform, which is also the reason why the attack works, is that we're running everything with top privileges. We can escape the payload isolation. We can escape the main experimenter platform. And in the case of a PSSAT, the SCPP is connected with the bus, is connected with the CCSDS engine. It's connected with with everything. It's basically the brain of the satellite. So we can definitely escape the isolation and do even more damage. For example, I can show you just one of the examples of the applications. This is an application that I find on GitHub, a successful application that's been deployed and run on OPSSAT. It was running image classification with machine learning on OPSSAT using the camera and the FPGA and the framework. And we can see right here, if we go a little bit into the code, that they're using the exact same binary that we were using to capture a picture. So if we were to deploy that library, if we managed to feed it to the linker and to the original binary, they would execute the code and run their commands and do their analysis on fake pictures or whatever we want them to do if we're not mean enough. So this concludes the demo. Yeah, the satellite experimenter platform has more functionalities. It actually manages to do a lot more, but for this demo, it's a bit out of scope, so we'll stick with the presentation so far. So what do you say about this? Well, what's the catch? Well, we're focusing a lot on ground station as a service security. We're focusing a lot on legitimate channels, like on illegitimate channels, like ROG channels. So in case we send commands from unauthorized ground stations to the satellites and whatnot. But we need to remember that, especially with the near future with satellites and CubeSats and small satellites in general, bigger satellites are going to be so powerful and so complex. We need to focus very much on the security of the spacecraft itself. We need to keep that in mind. So we want to develop these kind of software in this cool toys secure by design, because in this case, this was not really exactly what happened with the very relaxed permissions and very relaxed access control. We need to run penetration testing and audits on software on spacecraft, just like we do on software and IT infrastructure that we have on ground, because it's essentially what we're having is the new IoT revolution, and we very well know how that ended. It was not the greatest transition ever. We had a lot of vulnerabilities with IoT devices, and that impacted the critical infrastructure very much. And space is definitely a critical infrastructure. So the same way we increased and we take care of housekeeping, and we deal a lot with telemetry, and we take good care of telemetry of the spacecraft, we need observability and traceability of the software. So in this case, in the case of this attack, it would mostly go unnoticed because there's no actual log of the services used by the apps. So if people didn't complain, if experimenters wouldn't complain about that, I would be able to covertly run around the satellite and use more software and gain more privileges and do more damage, very likely. So yeah, this is mainly my point, and that's it for me. Thank you for listening.
All right, thank you very much. So, do we have a few questions for him? Oh. Yeah, I'm handling too many things, apparently.
Thanks very much. Really interesting talk. I wanted to ask a bit about the access control in terms of getting your library into the linker path. Is it currently the case that you need root privileges in order to do that for any user other than the user that you're currently acting as? And do you think that this could be worsened if, for example, the binary has like the set UID flag set?
Very good question, very technical, I like it. So in this case, everything on the platform runs as root. That's why the exploit is possible. That's why it could be weaponized and become even more dangerous. In my case, I showed it just for demo purposes with the LD preload trick, which in case you might know is how to explicitly tell the loader to link that library. But what I could do is spend a little more time crafting a different library and just overwriting the original one, because I'm root, I can write wherever I want on the file system, and there's not really anyone stopping me. Yes, so in the set UID trick would improve the attack if that was the case, but we're root already, so pretty much we can do whatever we want. It's a playground so far.
Can I ask a quick follow-up question? How does the payload isolation work, considering that you're root already?
Through obscurity mainly so far. I don't have, unfortunately, the diagram with me. It's not very clear. I don't know if you have. We maybe saw it yesterday. It's a huge diagram of the whole OPS set architecture, how it connects to all the older router systems, and it's all. Obviously, because it's very complex, it's all very interconnected with different protocols. We have I2C, we have CAN bus, we have the old bus system on the side. So effectively, it's just a matter of exploring once you're inside. So the title was a little provocative, maybe in that sense, as in the isolation so far has not been enforced. And so if it were enforced, then it would have had a bit more challenging. I know, for example, I put on the slide the new CubeSat mission that ESA launching soon, CYSAT, and the new version of the NanoSat framework address these vulnerabilities because they took care of access control way more. So on the Linux system, we have user-based execution, and that is very nice. It helps a lot with the attack. It would render it useless most of the times. So yeah, yes, I hope I answered. Yeah.
Brilliant, thank you.
Yeah.
All right, since we have a bit more time, one question from my side. Was this the first time that you exploited something on a satellite?
This case, yes, it was. It was, indeed.
So maybe you can elaborate to people trying to get into this topic. What was like the biggest challenge that you overcome during this? What was like the hardest part to get into this like whole satellite security topic for you?
Yeah, so as you said previously with my introduction, I've been studying cybersecurity for 5 years, so I'm not completely new to the cybersecurity field, but I am new to the space field. And it's been very interesting to dive into it. What I found, definitely one of the main challenges that has made the study and the attack, but also the whole setup, mainly because I spent quite a bit of time on preparing the emulation of the payload, is how horizontal the need for knowledge is. So it's not just being a good software engineer. It's not enough knowing about security. There's networking involved. There's different protocols involved. There's technologies that sometimes are open source, sometimes they're proprietary. There's documentation involved, which is usually not there most of the times. So I think it just takes a lot of motivation and a lot of grit to not give up when you see all those challenges stop you and like shout at you through the screen. It takes a little bit of crying on the computer sometimes. It takes a little bit of patience, but yeah, I would say there's nothing stopping you as long as you are curious to kind of work your way around things and work your way around problems.
All right, very cool. Yeah, thank you again.
Thank you very much. Thank you.